Okay, guys, let's jump back into 19. We're going to be focusing on that carbon nucleophile. I will start off with my acetone, but this works for any ketone or aldehyde that you're going to come across. And our first reaction should look really familiar to you. We are dealing with a Grignard. I want to go ahead and just use an R group here because you can add a wide variety of R groups this way with your organometallic Grignard reagent, followed up with something to provide protons. You're frequently going to see H2O. You might see H3O plus. In lab, we used ammonium chloride. What's really an important take-home message here is that there is a 1 and a 2 step. This cannot be a one-pot reaction. So if you don't put the 1 and the 2, you will kill your Grignard. So that's part of understanding this reaction. So make sure that you know it is a 1-2 reaction. We make an alcohol and we form a new carbon-carbon bond between the Grignard and our carbonyl carbon. Anytime we make new carbon bonds, we're pretty excited. That gives us a lot of, that gives an important tool for synthesis. If you start off with a ketone, you're going to make a tertiary alcohol. If you start off with an aldehyde, you're going to go ahead and make a secondary alcohol. We're not going to worry about stereochemistry. When we happen to make a new chiral center, and it happens with Grignards, you get both enantiomers because this initial attack happens on a flat carbonyl. It can happen on either side. We're going to quickly step through this mechanism because this is not new. You learned this in Organic 1, and we will see it again in Chapter 20. Right? But I do want to point out there's two different ways you might see a Grignard presented. You may see it like on the slide as though the R is the anion, the MgBr is the cation. It is a very, very polar, big difference in electronegativity, so that's not inappropriate. But you will also see it as a covalent bond, and just you have to recognize all of that electron density is being pulled towards the carbon, which makes the carbon into a good nucleophile when usually carbon's an electrophile. You want to make sure that that arrow is coming from that covalent bond or from the lone pair if you do the anion. The MgBr does not wind up in our product. So this, if you do show it as covalent, that bond breaks. To avoid 5 bonds on carbon, we move the pi electrons up and we form our tetrahedral intermediate. The final step, where the water comes in, provides a proton so that we can get our neutral alcohol product. All right. There's practice in your homework. There will be additional practice online. Make sure if you are struggling with Grignards in the past that you circle back around at this time and you brush up on them. Now, the next reaction, the cyanohydrin formation, is also very straightforward. This is a one-pot reaction. I'm going to go ahead and show this how you'll normally see it. It works with HCN because it's such a acidic solution here, and it works better under basic conditions. You are going to wind up with some KCN. It helps. Let's see, they explain it over here. To achieve the basic conditions, this salt can be helpful. I'm not going to ask you to write an essay on that, but I do want you to recognize the combination of reagents. You are going to make a new functional group called a cyanohydrin. Lots of new functional groups in this chapter. Your mechanism is very straightforward. The nitrile is a very strong nucleophile. And sometimes you'll see just CN, or you'll actually see the triple bond. You need to recognize that CN minus has a triple bond. You're going to have that nucleophilic attack and form your tetrahedral intermediate. And then because we have HCN, because we have an acid around, even if it's in a small quantity, right, that is going to provide our proton that will give us our neutral cyanohydrin product. Now, something that you don't necessarily see on the slides, but is important, is the variable acid situation. HCN is dangerous, right? It's toxic. There's a lot of hazards in working with it, and people frequently don't want to work with it. And since you really just need a catalytic amount of the acid, often you will see KCN paired with HCl. So you still have that proton to for that last step that you saw up here, but you don't have to work with HCN. The KCN is much safer, and you wind up getting the same product. So you should be prepared to see both of those reagents. Just like with Grignard, if you do get a chiral center, it will be racemic. That first step, you are attacking a flat carbonyl. So you could attack it from the front or the back, and so you'll get both enantiomers if, in fact, you are making a chiral center. Now, cyanohydrin formation is really interesting because it leads you to very specific spacing of functional groups. Two reactions that we are going to see in chapter 20 are shown here. You can reduce a nitrile, so you could get an amine. You can oxidize a nitrile and get a carboxylic acid, and it will put those functional groups on a carbon adjacent to the carbon with your alcohol. We're not going to spend a lot of time pondering over that right now, but be on the lookout. These reactions are coming, and we'll see them when we get there. All right. Moving right along to something a little bit more complicated, a little bit more interesting, our Wittig reaction. We also have had the opportunity to do this in the lab. We are going to start with an aldehyde or a ketone, and we are going to use a very specific Wittig reagent called an ylide. An ylide is your triphenyl, right? So there's 3 phenyl groups on a phosphorus atom that is attached to a carbon. This is your R group, essentially. This is what you're adding. Now, you will sometimes see this drawn as a double bond. I would say more frequently, you're going to see it drawn as zwitterion. So you've got a positive charge on the phosphorus and a negative charge on the carbon. That's what makes the good nucleophile here. All right, so you're going to have that ylide reagent, PH3P. There will always be a carbon here, and it will be attached either to 2 hydrogens, a hydrogen, and a carbon, or 2 different R groups. So right now I'm just going to leave those kind of like open bonds. You're going to wind up replacing that carbonyl, but you're still going to have a double bond, and it's going to be to that carbon that was attached to phosphorus, and then whatever was attached to the carbon. You have a couple of examples with generic R groups here, and then something specific here. This phosphorus ylide, there, as you can see, the 2 ways that you could be presented with it. Oftentimes in practice problems, you'll see this just because it's easier to draw. But either way, the carbon is more electronegative than the phosphorus. It's going to be pulling electron density. It's going to be your nucleophile. The reason that you'll often, that we talk about it looking like this is because the phosphorus and the carbon are in different rows of the periodic table, so the p orbitals involved in the double bond are different sizes, so you don't get as effective of an overlap. We are going to take a look at this mechanism. This part of the mechanism is what you're going to be responsible for Wittig. You still have your nucleophilic attack, and so I'm going to go ahead and draw this here. You have your, I changed my mind. You have your, let's see, your phosphorus with the 3 phenyl groups, and you have your carbon. Now again, whether you draw it from the bond or if there's a lone pair on the carbon, it depends on how it's presented. If we're looking at it like this, it's going to come from the lone pair on the carbon. Now, we can't have 5 bonds on the oxygen, But instead of making a tetrahedral intermediate here, because that carbon is attached to that positive phosphorus, that pair of electrons from the pi bond just goes into that empty p orbital on the phosphorus. So we actually wind up making this really interesting square intermediate where you have your new carbon-carbon bond, and you also have a new oxygen-phosphorus bond. The phenyl groups are still there, and whatever was attached to the carbon is also still attached to the carbon. Now, this is called an oxaphosphatane. It's a four-membered ring. As you might imagine, it's not super stable, so it does fall apart. If you think about the electronegativity here, carbon's more electronegative than phosphorus, and so the CP bond falls apart in this direction. Oxygen's more electronegative than carbon, so oxygen takes the electrons with it. And then we wind up with our new carbon-carbon bond. You also wind up with this triphenylphosphine oxide salt. That's what led to that sort of crazy extraction that we did when we looked at this reaction. Again, this is the mechanism that you are going to be responsible for. We are quickly going to go over how you can make an ylide. I just want to talk through it because this is a very, we get introduced to a really interesting and kind of sad molecule, at least in my life. You start with an alkyl halide and you treat it with the triphenyl phosphorus compound. You get an SN2 reaction here, and you make this phosphonium salt. Now, the phosphonium salt is very stable, and so you need to treat it with a very, very strong base, right? A negatively charged carbon is going to be a really strong reagent. It's going to really want to pull a hydrogen from somewhere. And so it is strong enough to pull that hydrogen there. That leaves you with that ylide, right? That carbon that has lost whatever that fourth bond to a hydrogen. These are really interesting compounds, the alkyl lithium reagents. They catch fire when they're exposed to air, so you have to be very careful with them. I worked with a tert-butyl lithium back in grad school, and I always had to use special PPE, more fire retardant gloves. I had to make sure people knew what I was doing. There was a very bad accident back in 2009 in California that really changed lab safety across the country because a graduate student in organic, unfortunately, was sprayed with some of this and passed away. So this is a reagent that you would want to be very respectful of. A lot of times we work with very toxic or wild chemicals on paper as we're learning, and sometimes we forget how in real life how much respect we need to give to those chemicals. This would definitely be one of those. You'd want to be very careful. All right, so for the Wittig reaction, what I want you to pay attention to in terms of quizzes and exams is I want you to know how to predict products given a carbonyl and an ylide. You don't have to make the ylide. You do not need to, I won't be looking for the stereochemistry, but that is something to pay attention to in your homework. Right? The Z alkene is favored if you have an asymmetric alkene that you're forming. So that is definitely a note to keep track of when you're working your homework. Let's see. We are not going to go into what about the exceptions to that. So I'm going to skip through that stereochemistry. We are also going to skip over Horner, Wadsworth, Emmons. So you're not required to know this part on slide 69, which goes into 70, 71, 72, let's see. No, this is just a Wittig example. Because it is an SN2 like reaction here, sometimes you want to be thoughtful about which parts of your carbon chain are part of the ylid or your ketone. That's something that if we had more time we would look into, but just know how to predict the products and do the mechanism and you should be gold. Okay, this is what it would look like if you were asked to do the whole synthesis, starting with the alkyl halide, making the ylid, and then right here would be the Wittig reaction. This is the portion that you're going to be responsible for, right? Just the Wittig at the end. I think this is the last bit, and this is where we're going to wrap up. This is a little bit different reaction than what we've been looking at. It's not a carbon nucleophile, but it fits in because this is a reaction that is specific to aldehydes and ketones, and that's the Baeyer-villiger oxidation. It's almost like a perfect entry into the next chapter, which is all about carboxylic acid derivatives, because it gives us a way to convert an aldehyde or ketone into a carboxylic acid derivative, either a carboxylic acid itself or an ester. It very specifically uses a peroxy acid. You have used peroxy acids before when you made epoxides back in Organic 1. So it's a functional group that it shouldn't be completely new to you, right? If we take a look at it, it's like a carboxylic acid, but it has an extra oxygen. What happens when you treat an aldehyde or ketone with a peroxy acid is an oxygen inserts itself between the carbonyl and either a hydrogen or a carbon off to the side. So it allows us to access esters and carboxylic acids this way. It is an interesting mechanism that you will not be responsible for. If you just like to look at different mechanisms, this certainly is one. Again, you will not be responsible for that mechanism. This works if you have a cyclic ketone, right? It can insert that oxygen, just like it could over here with acetone. In this example, and the example that I have over here on my whiteboard, we're looking at symmetric ketones. So whether I put the oxygen on the left or the right of the carbonyl is irrelevant. It's going to come up with the same answer. But what if we have something asymmetric or we have an aldehyde? Which side is the oxygen going to go? And here is your guide. This is something you need to memorize. It will go to the side with the hydrogen first. So if you have an aldehyde and you perform Baeyer-villiger, you are always going to wind up with a carboxylic acid. Breeze would just like to say hello. All right. However, if you have a ketone and it's asymmetric, okay, hang on one second. I don't want to re-record. Breeze. Shh. Hush, bud. There we go. Okay, just a little mid-recording dog show here. If you do not have an aldehyde, you have a ketone, you are going to put that hydrogen on the more substituted side. So if we have something like this guy, right? What is that? A 3,3-dimethyl-2-butanone. If we treat this with our peroxy acid, we have to be careful here. We have 1, 2, 1, 2. Now that oxygen is going to be here. And then our carbonyl. One side has to flip over, right? One of the most common mistakes with Baeyer-villiger is people wind up with products that have less carbons than they started with. We do not take anything away from this. We just add an oxygen. So if I have 1, 2, 3, 4, 5, 6 carbons, I should have 1, 2, 3, 4, 5, 6 carbons at the end. This is an excellent reaction. I give you a ketone to start off with, but I want you to perform a reaction on an ester, this reaction gets you to that ester very easily, very smoothly. All right, so you have some additional examples here. right? Ketones, more substituted side. Aldehydes, always going to make the carboxylic acid no matter what's on the other side. And then we come to 19.12, 19.12. This is at the end of all of your Klein chapters that have new functional groups and lists of reactions. This is for you. This is to help you with additional synthesis problems. We are going to have a synthesis lab soon, so I'm going to leave these slides with you guys. I will tell you we aren't doing anything new with spectroscopy. Everything we were going to do this semester with spectroscopy, we did. So you can skip over the spectroscopic slides. That will come up again on the final, but again, only what we covered previously. I love these kind of slides. You just get a big review sheet from Klein. You can print this out, white out the reagents to help you go back and practice that. You can white out the products and practice predicting those products. This is a great review slide.